Now that we're back used to differentiating and integrating while working with mechanics and our kinematic motion variables, we need to make sure that we can still do this in vector form. So if our variables are presented in vector form, they have two components, the horizontal and the vertical, the I component and the J component. We should still be able to manipulate these through calculus by integrating and differentiating. So let's have a look at an example here. A particle P of mass 0.8 kilograms is acted on by a single force F. The position vector of P at time t is r meters, and we've been given the function of r. We've been asked to find the speed of P when t equals 4. Okay, so let's just start there. The information we have is that the mass is 0.8, and we have the position vector, which I'm going to write in column vector form. Speed is related to velocity. I can find the velocity function if I differentiate this position vector. So v is going to equal dr dt, and I simply need to differentiate the horizontal component and differentiate the vertical component. So I've differentiated those separately, but still written them as a column vector. So this is the vector for velocity. Let's find the velocity when t equals 4. I'm just going to substitute 4 in place of t. And here we have the velocity vector. Okay, the question asks for more than this. It wants the speed of p. So we need to find the magnitude of this velocity vector. To find its magnitude, we're going to apply Pythagoras. And this goes straight into the calculator, and we get an answer of 96.1 newtons. So this was the speed of P when t equaled 4. We started with the position vector, which we differentiated to find the velocity vector, and then we had to find the magnitude of that velocity vector. So in part B, we're asked to find the acceleration of P as a vector when we know that t equals 2. To find the acceleration, we're going to differentiate the velocity function. So we get 12t, and we get 75 over 2, t to the negative 5 over 2. Okay, let's substitute t equals 2 to find our acceleration vector. And here's what we would get as an exact vector. And to three significant figures, we have 24, 6.63. In part C, we're asked to find f when t equals 2. Okay, so once again, we're going to make use of Newton's second law, so F equals ma. When t equals 2, well, we already know the acceleration when t equals 2. We found that in the previous part of the question. So we just need to substitute the mass and the acceleration vector. So mass is 0.8, and we substitute our acceleration vector. We get the vector of the force being 19.2, 5.3. So a similar expectation to what we've had previously, but we should be really comfortable in working in vector form, in manipulating both the horizontal and the vertical components separately, but making use of them together in a vector. If we're then asked to turn that vector into a scalar, as in speed or distance or even acceleration, we know that we can transform that vector into a scalar by using Pythagoras.